Yeah, and then you should start the recording then also.
Yes, just to be sure. So thank you.
Fine. So let's just make a very brief, quick repetition, and then I will show you a number of examples related to what I've shown before we continue the final part of this. Maybe some of it will be also given on Tuesday. But actually, I have a number of, I find quite interesting examples on Petri nets and the relation to automata, reachability graph, and etc. So just to repeat here that a Petri net is defined by especially these A+ and A- matrices, which means that you define the input and output places to the different transitions, and there is a specific equation here which updates the marking vector. So what I would like to show you now is an example where I give them A+ and A- matrices and also the initial marking, and then we should generate a Petri net based on this. And then there are some specific questions on here, let's see, show that the number of tokens in the second and third places can increase unboundedly by evaluating corresponding reachability graph. Yeah, that's an interesting aspect generally for Petri nets, that they can also handle infinite state systems, which of course generates problems on decidability and so on. But Petri nets are with some restrictions decidable, but I mean, in practice it's not so interesting to look at this, but there are some theoretical aspects on this that are of some interest. So then the final remark here is add an additional so-called control place in the Petri net to avoid that the number of tokens in the second place can be more than one. Verify this by evaluating the reachability graph for the modified Petri net. So we first see here that there is one transition where you have two output places for that, and the third place is an output place to the second transition. But okay, I think this is defined also here, so we can look at this and see that the output place in the first transition is both back to P1 and also to P2. And the second transition has an output place P3. And the input place to the first transition is P1. And the input place to the second transition is P2. So these two matrices define this Petri net. But then there is an interesting behavior here, namely that there is no restriction on this T1. It can continue forever and produce more and more tokens there. And we can see that by generating first, we see that the initial token is only in place 1, 1, 0, 0, no tokens in the second and third. Then we can generate by going downwards here, we generate more T1 transitions. In that case, you get, you could say that by T1, you actually don't generate more tokens in P1, it's in P2 we generate more tokens, which you see here. Because in in T1, you take the token from P1, but you give it back. So it's this kind of self loop. But T1, when it's executed, you can get a token in P2, and that can continue forever. So that's why you, if we go downward here, you get first 1 token, then 2 tokens, and 3 tokens, etc. Then with the second transition, we can go in the right direction. And then you see that by the second transition, you just move the tokens from the second to the third place. So for instance, in this case, when you had 3 tokens in the second place, by repeating the second transition, you take away from the second and move to the third place. And after 3 transitions, you have no token more in the second, but 3 in the third place. The number of tokens in P2 increases without bound, since T1 can always be fired. The number of tokens in P3 increases without bound as long as there are tokens in P2. And then the question, how can we restrict this behavior? Because maybe it was not the meaning that we should have this kind of system. So what we can do then is that we add a control place. You remember that I added a number of control arcs before, but now we also add a restriction on the second place, simply saying that, okay, if you execute T1, you add 1 token to the second place, but after that, you cannot do anything more because this T1 transition requires 1 token from P4, and you have to move that token back again to repeat this. So you could say that adding this type of restrictions on any place with adding a transition within a complementary place where the input transition to P2 is the output transition for P4 and the opposite. In this way, you bound the P2net. In this specific case, you bound the second place. So that means that M2 can never be more than 1. And in that way, we can also see that the possibilities you can achieve here are that, okay, you start with this initial marking, and then by executing T1, you get 1 token into P2, and no one more in P4. But then when you execute T2, you get 1 token in P3 and 1 back in P4. And then you can repeat this again. And by this, you could say that at least we have restricted the number of tokens in P2. But to be honest, we can continue this forever and increase still more and more tokens into P3. So we haven't bounded P3, we have only bounded P2 with this procedure. Okay, so this was typical behavior and analysis, especially this, including this bounded places. It's a technique that is quite common. So you expect that you have a bounded capacity of machines and buffers and so on, and that means that you have this supplementary or complementary place, which gives, so to say, more rather model the number of empty parts, empty places in your original place, P2 in this case. Okay, any questions? Let's see here. I wasn't hear any sound before. Okay, I think this is solved now. So then we go on with another example which illustrates a little bit of this possibility to add control arcs to limited behavior of a system. So in this case, the question is to generate the reachability graph for this Petri net, and we should also identify any blocking states. And actually, there will be some blocking states in this situation. You could maybe realize that it's a little bit of this reverse order booking also in this example, as I showed you in an earlier one, where we also got deadlocks. But now that the difference is that I have two R1 resources, I have two tokens here. So that brings a bit more flexibility, but also complexity. So then we should avoid these blocking states. We'll find by adding arcs and optionally also places. Motivate your solution is maximally permissive. That is, your solution only removes the blocking state, but no non-blocking states. Okay, this was actually this is quite a hard work to generate all this this complete reachability graph, and it's easy to get a very unstructured solution, so to say. But you see here that with some training and maybe I even looked at some solutions from students, I could generate this solution. And here you could find that, well, there is actually only one blocking state in this system, because for all the other, in all the other situations, you can continue and reach from the initial state, the marked state. I will not give you a comment on the details here. We can just say that okay, you can, for instance, make an A1, and in that case, remove the number of tokens in the first place up here with 1. So you could say that the states I show you here, the numbers here 2, 1, 2, 0, etc. These markings are not complete. I don't mention. Oh, sorry. Now I see. What I take as the state information here is the number of tokens in R1 and R2 and M. That is what is shown here. And then you see specifically here that in the blocking state, there are no tokens back in any of the resources R1 and R2. And that is the reason why this is a blocking state. But okay, here you also have 0, 0, but you can continue. So it's not always that is the case. So you can go through this yourself and follow the steps how to generate this reachability graph. But now the more interesting question is, can we reduce this system to avoid this non-blocking state? And you could see that the situation arises when you have generated 2 A1 and 1 A2. So either A2, A1, A1, then you get into the blocking state, or A1, A2, A1, or A1, A1, A2. So it means that we need to restrict the behavior of A1. So this control place actually say that if you have done 2A1, you're not allowed to make another A2. If you have come to this place or this state, you're not allowed to make an A2 before you must continue with a B1 instead. For A2, or let's say when you have made A1, A2, then you have also consumed the 2 tokens here. So you have taken 1 to A1 and 1 to A2, and then nothing more can happen. It means that both A1 and A2 are blocked, so to say. Okay, you can take a more detailed look at this, but this is a so-called control place which restrict the behavior. And then, of course, one could discuss how can we is it possible to generate these control places and control arcs automatically? And there are some machinery or some algorithm to do that. You could also see here that, I mean, compared to the automata, the total automata description of this, of course, this is much more condensed information in the PetroNet once again. Let's see if I had something more. Now, okay, then I'm coming with some more examples later on. And here you could say that this is really a planning problem where we have a number of operations that we would like to perform. And the idea here is that, well, there are some preconditions for these different operations, and planning is typically that you have a set of operations and you want to perform these operations, but to perform those operations, you often have some conditions that must be fulfilled to start a specific operation. And in this figure, I introduced 2 ways to describe a precondition. First, let's take this one. To start O2, O3, the operation O3 must be completed. But to start O4, even O6 need to be completed. It's not enough with only O2. Also, operation O6 must be completed or finished. So it's made some comment here saying that I assume that I have a variable related to this system here, where the variable can take has one value or one state here corresponding to OFK. And you also see that the second operation also has a restriction related to O5. So O5 must be completed or finished to start O2. Actually, you see that this these sequences here, the preconditions are, it is just another type of graphical model than we have seen before. It has some flavor related to, you could say, extended finite automata and also PetroNets. It's obviously a parallel behavior, but you see that U2, you can see in 2 of the sequences. So that means that the operation O2 has actually 3 preconditions, both O1, O3, and O5. And of course, I could also have tried to put some arrows from both O1, O3, and O5 this operation O2. But the idea with this type of description is that it should give, it should emphasize on the operations and sequences of operations, but still be able to add some additional preconditions without getting a too complex graphical model. So these sequences of operations was something, and the formulation on related to this was something I formulated, say 10 years ago. Okay, so we should first formulate a PetroNet and then an alternative modular system with automata. And then we should also show by making a reachability analysis that it's possible to reach the final state. And that is given by a specific event of strings, which you could say also is related to what you can execute, what you can get from the PetroNet as well as from the automaton. If you have a correct solution, you should then, of course, generate the same language. Let's look at the solution. I introduce here labels or event labels SI for start of operation I. So in this case, I start operation 1, and C means complete operation 1. And you could say that operation 2, the start of that, has a number of conditions here, and also that S4 has a few conditions. It would have been nice here to see them all together, but okay, we say that we focus specifically on O2, and then O3, O1, and O5 need to be completed to start O2. And then we see that, yes, operation 1, which is this part of the PetroNet, it must have a token here to be able to make the start transition in the second operation. And you also need to have a complete token in 3 and in 5. But you see here that the technique here is that these are conditions on the start of S2. So it means that you just ask for a token, but you immediately give it back again. So it's a guard, you can say. And then S4 had S2 as a condition also, and S4 actually had both operation 6 and 2 as conditions. Let's see. Operation 4 has 6, but also 2 as condition. Yes, that's right. So by this, I formulated now a PetroNet. And in this case, one could, of course, discuss if this is extremely readable or not. But yeah, I would say that what I will come up with later is these variables, which actually can be used. You can, for instance, in this case, introduce a variable here for that state. Let's call it final state 1, F1. So then F1 is equal 1 or F1 is true is a condition, as well as F3 and F2. So F1, F3, and F5, is a condition to start the second operation here. And generally, we can say that logics is not that very good to describe by these arcs back and forth. So you soon get what a very famous professor in Petri nets, he said, oh, you mean the spaghetti when you get too many arcs back and forth. And we would like to avoid the spaghetti. And my solution to that is to add instead variables generating or representing the logics of the system. And the logic are these preconditions. Okay, then we can also describe this by simple automata that are shared and or synchronized. So we can look, for instance, specifically at S2. That requires that C1 has been executed. So that means that C1, you could say that here you have that C1, C3, and C5 must all be executed, and then you are in these states. And then S2, as a synchronized event, can be executed in all three of these automata. In the same way, S4 can be executed when both operation 2 and 6 have been executed, and operation 6 has a precondition that operation 5 must be completed. So based on this, we can also generate a possible sequence of operations of start and complete operation here. And one could easily see that, for instance, the first, the third, and even the fifth have no conditions. So we can start with them. S1, C1, S3, C3, S5, C5. And when all these have been in the completed state, you can execute S2 and also complete that. And then you have done enough to also execute operation 6. And operation 6 is a precondition for S operation 4. So here the sequence is that we start with operation 1, 3, 5, and then 2, and 6, and 4. But this is not the only solution. This is not the only possible sequence. For instance, you can start all three of these operations, S1, S3, and S5 at the same time or in any arbitrary order. And then when these are completed, C1, C3, and C5, you can start S2. Actually, to start all these three operations at the same time, not exactly at the same time, but you shouldn't wait for S3 to start until S1 or operation 1 has been completed. So in that way, try to start as much as possible. It generates, of course, a much more efficient solution. And here we come with optimality also in terms of trying to find the most efficient say time optimal sequence, and it's obvious that C4 is the final event that will happen. So to be able to execute C4 as soon as possible could be considered as a goal for this. Then another example, you have to break me if you have more questions. So if not, I continue.
Hello.
Okay, no question?
Yes, it seems.
Or? Yeah, I go on with this next task here. For a resource R, give the formal language as well as the mark language well, this is a repetition of what we looked at before, but after that comes some PeterNet aspects. So first, give the language of the resource, which is a bit more complex than for this machine, which is just B, E, C, and then repeat that. Here we have C followed by D, or A followed by B, and then repeat this. Formulate the PeterNet for the synchronized system R synchronized M, including the marking vector for the synchronized marked state. Yeah, I mean, the marked state here is that both R and M should be in the states 0. And then we should, based on the PeterNet, also generate the automaton R synchronized M by generating simply the reachability graph for this for the PeterNet we get when we synchronize R and M. And then it looks like there is a small problem here. So add one or more arcs for R and M to avoid the blocking state. So what we will find when we have generated the automaton R synchronized M is that there is a blocking state. Let's see. The language for the marked language, we can say for the resource is not that difficult. It's A, B, or C, D, and then you repeat this by the star operator. But the complete language also includes the events that happen in between you are in the marked state. So you must also represent a situation where you are in state 1 and in state 2. And that is picked up by writing, okay, you can go around and go back to the marked and initial state. And then you can stay there with epsilon, or you can make an A or a C. An A brings you to state 1 and C to state 2, if I remember correctly. Yes. But then you have described state 1 and state 2, and you could say that looping around and bringing you back to state 0 is captured by this part of the language. And then, of course, all prefixes of this. That is the complete language of the resource R. So you see, it's yeah, I mean, it's not very difficult, but it's not totally trivial either to generate the complete language for an automaton. So now we should generate then the automaton, the PeterNet for this system. And well, maybe it looks a bit more complicated than we expected, but let's take a look once again on first the machine, which was B, E, and back to C. And that we can see here, B, E, C, and then back to B again. And you could say that this is the initial and marked state. Now B and C are shared with the resource, but not maybe the ones we expected. It's not the first, it's not the, so to say, booking event. You could say that the C event is a booking event because then the other part, the other alternative cannot be booked, so to say. But here the synchronization is that C and B are synchronized. So it's the return on the resource in its other duty that is synchronized with this machine. And actually, I found a practical application on this where you could say that in a situation where you use, for instance, a robot to bring something to a machine, and then the machine can work independently, and then you use the same robot to also take away a part and synchronize with some coming buffers or resources after that sequence, working with the machine. So without telling you all the details here, this was actually a nice and for me new example. I was not aware of that this situation can generate a deadlock, but there are practical relevant resource booking applications where this type of behavior could occur. So remember, once again, it was C and B that are synchronized. And then we can see here that the resource R can be either in its idle state or make an A and then synchronize with the event B with the machine M and then go back. Or it can take the C event, which is once again shared with the machine, and then independently locally take a D and go back. So the init and marked vector is the following one. You have a token in the first place and in the last place, P6. This is the initial and marked vector. Now we generate then the reachability graph of this system, and we start with, we can say that the states we see here, 0, 0, is the 0 state in R and the 0 state in the machine. Then we can take an A, and that means that let's see here, then it's the resource, the robot. The robot picks up a part and deliver that to the machine. And then the robot is free. But then it can also support this machine bringing a piece from, let's say that was AB. But then the machine can take an E, which we can consider as an operation within the machine. And after that, we are in this state A2, 02. That means that the robot is free and the machine is in its second state. And then you can take a C with the robot and a D and go back again, and that's fine. But when the machine is in this state, when the token is in this state, when the E has been taken, if then the robot starts to deliver a new product here, you will come into a deadlock, because then nothing more can happen. Because the problem is that the robot has already put a part before the machine and it's busy. The robot is busy. So it cannot at the same time remove a part from the machine. And that's why this blocking situation comes up. So it's important that before the robot upload a new part, it must move away the current part in the machine before it makes an A, meaning that it picks up a new part. So this A event you have to be careful with. And this is very simply fixed and avoided by introducing this control arc, because A is only allowed when the machine is idle. So this is a control arc that avoids the blocking state. Executing A is only allowed when the machine M is free in state 0. And once again, this was for me a situation which I haven't realized before, but I found that in that example in an interesting book. Otherwise, you can say that there are a couple of standard examples of when deadlocks occur, and the most simple and the obvious one, the most well-known one, I would say, is this booking in reverse order, or using two resources in reverse order. That's the classical problem. Actually, I haven't seen this example in any other textbook except in a specialized book on Petri nets and manufacturing applications with one of my nice colleagues, Bengt. So that was one more example, and now I've shown you two examples which I mean has some practical background. This is absolutely, in my view, okay, it's a tangle maybe towards my interest, but this is absolutely a concept which is a part of the planning literature or planning problems. You have a number of operations you would like to perform, and you have a number of preconditions. How should you make this plan so you satisfy all the preconditions and at the same time generate a possible sequence of events? This is the basic planning problem. And then the result is something like the sequence string of actions. And of course, then the optimal solution is of interest. But sometimes in the planning literature, people don't ask for an optimal solution, the best solution. They are just satisfied if you can find one solution. And what I gave you here in task C, 5C, was one specific solution. The next example here is on the coordination between, I mean, using, say, robots together with machines, or, I mean, it's not only robots. It could be, for instance, AGVs that are serving auto-guided vehicles in plants, or in big logistic areas where you have, say, a lot of containers and so on. Then this type of problems can also occur. Actually, for AGV problems, the deadlock problem is a real problem, because one of my former PhD students, he is now working at an AGV company here in Gothenburg, and another PhD student is working on another. We have a couple of AGV companies here in Gothenburg because we have so much of vehicle industry here, both Volvo cars and Volvo trucks and so on. And for these AGVs, it's quite easy to come into deadlock situations. And then this type of solutions and strategies can be used to, and modeling behavior can be used to avoid those deadlocks. Yeah, okay, one more example. In this case, we should reformulate this Petri net as a number of synchronized modular automata and formulate a set of synchronized modular automata when there are 2 tokens in place P1 and 3 tokens in place P21. Okay, so yes, I mean it's the question of the number of tokens in the initial places. So 2 tokens in this and 3 tokens in P22. Let's see how that can be done. So you could say that this is a modeling problem. Actually, the type of models you see here, we have seen before, definitely. For the R1, it can either take an A1 followed by C1 and then beam back, or B2 followed by C2 and then back. Let's see if that's correct. A1, C1, or A2, no, B2, C2. And that is exactly what you see for R1. A1 followed by C1, and then you are back in the initial state. Here, the resource R1 is now used for one specific task, for actually the left sequence, and with this model, it's used for the second sequence instead, the right sequence. And corresponding for the second robot, it's there you have B1, C1, A2, C1. The second robot is used here, related to this place P13, or you use it from A2 until C2. So in that case, in the second task, it's used for 2 places. Then you have the Petri nets, or the automata for the 2 sequences, one for the left and one for the right sequence. So the total system is then P1 synchronized R1, R2, and P2. And of course, here one could discuss which one of these models is best to understand this behavior. But I would say that probably this is still more readable. But with this modular description, it's absolutely possible to understand the behavior by looking at the individual models here too. The problem with the Petri net is that soon you get a lot of arcs back and forth, and that could make it a bit difficult to understand. Assume, for instance, that you have 3 or 4 or 5 sequences with flow of tokens. And then say R2 is used in the 5th sequence. Then you have to write a lot of arcs back. Not a lot, but arcs that are long and so to say disturb the picture. So it can once again be quite difficult to get the message. In that case, I would say that this type of model can be equally or even better to read and understand. And once again, even better if you introduce what I propose, namely these variables, which I introduced in the afternoon, sorry, where I had this R plus and R minus and B plus and B minus and so on. So to introduce a situation where you have more than one token, how can you do that? Well, I would say it's not exactly the same model as here, what I propose now, but it's definitely a model that works in the same way. I get some additional information by this model because here I introduce one automata sequence for each token. So that means that I have more information in this model than I had in the Petri net. The Petri net just tells us that from the beginning you have 2 tokens, and then which of them that is moving down here and in which order I have no knowledge about. I only know that say there could be, for instance, one token here and one token here, and which one I don't know. But then it's also an interesting, just short remark that an extension of PetroNet is what we call colored PetroNet, and in that case you can introduce color or identity on the different tokens. So then you could have a green and a red token, and then you can of course follow the green tokens transformation and the red tokens sequence. And what I say here is that a colored PetroNet corresponds to these individual automata. Let's say that P11 is the green and P12 is the red version or the red token. And then, of course, now you have more of booking events for the individual ones, and that means that the resource needs to be extended with a number of more bookings, and you see that resource model soon becomes a bit messy. And for the second sequence with 3 initial tokens here, there are of course then 3 corresponding automata. And also in that case, your resource needs to be extended. So in this case, the total system is P11, P12, and R1, R2, and P21, P22, and P23. The last 3, they represent the 3 initial tokens in the right sequence, and the first 2 automata represents the 2 initial tokens in this sequence. So you see here that there is a close connection between PetroNets, especially for this structure at least, and automata, but specifically modular automata. In this case, what is the question then? Generate the reachability graph of this PetroNet and identify the blocking states when this initial marking vector is also the marked state. So we would like to come back to this situation. Yeah, can we even see here that we have a deadlock or blocking situation? Well, I'm not sure I can see that. Just by looking at this net. There is a kind of so to say reverse order here, which you can see a little bit of that, yes. So then add a minimal number of resource tokens in the places R1 and R2 to avoid the blocking states and show once again the reachability graph to the modified PetroNet. Based on the results above, determine a resource condition without formal proof which guarantees a non-blocking system when the number of initial tokens is n instead of 2 in the places above and above the events A1 and A2. So I would like to achieve here a condition on how many R1 and R2 R resources are required if you have n tokens up here and here. So when I read this now, I get the feeling, oh, this was a little bit complicated problem. Let's see. So first, for this, we generate the reachability graph. And here, what are the states here? Well, it's 2, 0, 2, 0. Yeah, I would guess that, no. Aha, okay, sorry. You could see that here I have 2 tokens in the first place and no one in the second place, and the same for the second sequence. So here you have the tokens in the left sequence and in the right sequence, and here you have the number of tokens in the 2 resources R1 and R2. And going through here, we find that there are totally 9 states. And actually, in the last state here, there is a blocking state, while no other state is a blocking state. And the blocking becomes true when there are no resources available. Then you have the blocking situation. Okay, so I say here simply that add 1 token in the place R1, and I can show that I avoid the deadlock. Or no blocking state is also achieved when 1 token is added to R2 instead of R1. So it's obviously here it's enough that you have 1 more token in either R1 or R2. And by that, maybe we can find a reason. I mean, here the deadlock comes because you have 2 tokens up here, and if you add 1 more token in R1, that means that, okay, one could at least argue that it sounds reasonable that if you have 1 more R1 token, then the number of tokens up here. So n there, and n plus 1 here, or n plus 1 there should solve the problem. Let's see what the solution says. N tokens in the initial places above events A1 requires n plus 1 tokens in R1 and n tokens in R2, or n plus 1 in R2 and n in R1. Just to say this without more analysis could be, of course, discussed. But if you look at the structure of what happens in this automaton, you can quite easily see that okay, it's possible to extend this, and in that way see that, okay, if you just have 1 more event in the final state here, in the lower left corner, lower right corner, sorry, then it's okay. So then I've given you some examples on how we can reason, how we can make analysis. Okay, the computational tools here are, of course, that, say, for instance, in this case, I mean, if you have a given Petri-net, you just implement this equation and guarantee that you go through all the reachable states, and it's typically it's recommendable to generate a breadth first search also in this case. So this is something that you can implement yourself. Then we can continue with these extended models where we also now include variables. Maybe we should take, say, a 5-minute break before we take the last part, or? What do you say? You are there, or? Hello.
Hello?
Yeah.
Yes, sir.
I just proposed that we could take a short
Yeah.
5-minute break before we take
It's
the
okay.
last.
It's okay, sir.
Yeah.
Uh,
And if you have any questions, please please add them to the chat, and
Chat.
we can have more discussion. So let's start 10 minutes. Yeah, okay. What is it for now? You now? You sorry, I should add
1936.
4.5.
Yeah.
Your time is something 35. Is it
Yes, 7:30.
7:45 p.m.? No, yeah, okay. Isn't that right? Your time is 1935.
Yes, 36. Yeah.
Yeah. So 1940, and then we go on for 20 more minutes.
Sure.
Good. Okay, I got a good question here. When there are alternative solutions, then do we quantify the performance and decide the yeah, okay, now I got it. Yes, yeah. Yeah, I will make a comment on that when we start. So then we can start again.
Yes, we can start, and
you start
can we? Yeah.
Recording.
Yes.
So we have got here two good questions. When there are alternative solutions, do we quantify the performance and decide the final sequence of net? Okay. Yeah, first, I mean, if there are alternative solutions, then of course, and I would say that in most cases, there are alternative scenarios. So in some cases, I maybe find it a bit surprising that people are satisfied by saying, okay, I found a solution and I'm okay with that in planning problems. Because I mean, that solution could be actually very bad. For instance, the application or the solution I suggested with this sequence of operations I was talking about was actually a very bad solution, because I mean, what I wrote out was that you take the operations in sequence, although they could be made in parallel because they had no connection to each other. And of course, if you can make a parallel work, that's much better, because then you can make things much faster. So to get as much as possible in parallel or in concurrency is of course critical. So yes, I mean, to realize that you have a number of solutions and to find the best solution is critical. And that is exactly what I'm looking at myself right now. So I hope that on Wednesday, I will be able to tell you a bit more on the paper I'm trying to write now. I'm not sure if I will be able to complete it in time, but I have a deadline on Tuesday on that. So then I will tell you a bit more about how we can make these optimizations, including some abstractions and so on. Can these networks and automata be generalized to incorporate more events? Yeah, of course. I mean, I would say that a model is just a model, and if you would like to extend the model and you find that, for instance, I mean, there are two typical situations for the type of problems I've looked at now, because many of these planning problems are that you have a sequence of operations or sequence of tasks you would like to perform, and then you have a number of shared resources, and you would like to use these resources as efficient as possible, and typically to reach a final state as fast as possible, and that is in the scheduling literature called make span. I mean, the total time for the sequence of parallel operations is the make span, and we try to minimize the make span. And for that, you can use many different types of optimization strategies. Typically, this is formulated in operation research by formulating mixed integer linear problems, and they can be solved by branch and bound solutions, etc. And in that case, you could say that just adding, for instance, one more resource, which could help you to make things more efficient, is possible. And then you introduce both more events and more states. And it could also be that you, for instance, get a new task that you would like to perform within an existing, say, system factory or something like that. And what you do then is just that you add a new sequence of operations to the existing ones, and then you try to find maybe a new good solution for that. So yes, there is a total flexibility, especially when you have this modular structure, because then it's just that you can add one more model, and of course you can also modify existing models. I hope that was clear. So by that, no more questions. Yeah, thanks. I would like to give you some more examples now on these variables that you can add to automata and also to PetriNets. So this is quite similar example to the one I had here, which I presented in detail. What we will do now, let's see, is the following. First, I explain a little bit on this R plus and P plus and blah, blah, blah. And then I say that you should generate a reachability graph given these three extended automata with variables. And in this case, there is a blocking situation. Actually, there are two blocking states can be observed. And then we ask another interesting thing, and now we are really on the practical side here, because, I mean, if you find problematic situations, yes, then if you go for PetriNets, you can add these arcs, but I would say that it's a little bit complicated to do that, at least for more complex systems. But to add guards to these EFAs here, then you have quite nice computational tools to do that. So here is just an example of how things look like here. So what do we see here? It's actually the states of the three automata. Let me see if that's correct. Yeah, because here you have in the end 4, 4, 4, which means that you have reached all three EFAs have reached their final state. So this is the marked state. I could also have introduced the variables, the values of the variables as information in the state, because as I did here, then it's more clear exactly which possibilities we have. But in this solution, I didn't do that. What is interesting here is that if you make first a P plus and an R plus, you immediately get into a deadlock. And of course, one could ask why. Well, I think that the domain of these variables are 1. Yeah, and in this case, all variables only can take 0 or 1. So you could say that the variables here could be considered as Booleans. So here actually we have, looking at this, one could actually see immediately, yes, here we have a problem, because this is a booking of R and P in reverse order. Here I first make an R plus, I increase R from 0 to 1. And if I do that also for P, then it's both, here R is 1 and P is 1. And then the next state in G1 is to increase P further, but that's not possible because it cannot be more than 1. And in the other one, it's asked for increasing R, and that's not possible either in this when you are in this 2-2 state. So yes, here you have this reverse order booking, which makes it impossible. So first you must make R plus P plus in the first or P plus R plus in the second. And that's exactly what you see here. Then you can continue like this. And then there is obviously some other conflict, but it's once again related to this P plus and R plus, but in this situation also combined with a Q minus. Sorry. Yeah, because here you can make R plus and Q minus at the same time. But the critical thing is that if you make R plus and P plus and combine that with P plus R plus, then G2 and G3 can also get into this deadlock situation. Yeah, okay, I was a bit, yeah, now I see, aha, yeah, okay, exactly. In this case, the first automaton has reached the state 4, while the other two automata are still in their 1-1 state. And then you have the same problem as you had here. 11, 12, or 21, 22 generates the deadlock. And here you also have 11, 21, 12, 22 deadlock. But it's in the second case here, it's the second and third model that generates this problem. And in the case up here, it's the first and the second model which generates this problem. Otherwise, it flows. So you can generate, you can achieve the final marked state. So what can we do then to avoid this? Well, it's actually enough to then add a restriction in the first state. So here, for R plus, to do that, you must be sure that P is still 0. R plus and P0 is then an extra guard. For G3, it's also R plus and P0, while for G2, it's P plus and R is equal 0 instead of P is equal 0. So in this case, it's simply that to be able to make this R plus, you must be sure that the second EFA has not made its P plus, because if that has happened, then an R plus means that they arrive into the 2-2 blocking state or deadlock state. And also here, in the relation between G2 and G3, if you add, because the conflict is between R and P, and here you have the other one. And if you here say that, okay, P plus is only okay with if R is equal 0, it means that neither G1 nor G3 has executed, so they are in state 2. You could also say that you could also relate to the states here, if you like, but it's easier to relate to the variables in this case. Yeah, okay. By adding these extra guards, we have simply solved the problem. And that shows how easy it is to use or useful it is to use these guards also in the implementation of your control function. Otherwise, you could say that just skipping these states, the remaining automaton here is actually a supervisor, can act as a supervisor. But I mean, that supervisor includes 1, 2, 3, 4, 4, 8, 12, 16. It includes 20 states instead of just adding these 3 guards, and you have solved the whole problem. Now, I wouldn't say that it's always so easy, but definitely to instead of taking these supervisors as the final control function is quite often not the best solution, especially not if you should implement this in a PLC, because in a PLC, to have these variables and adding these guards is extremely simple. So for a PLC solution, this is absolutely perfect strategy. And then, of course, the question is it possible to have those kind of, to generate those kinds of guards? And yes, there are even in our tool Supremica methods to do that. So now I come up with another way to, yeah, this is a little bit, you could say that this is an introduction to the thing which I will talk about more. I think actually that we take this example next time, because I will give you some more background to this. So here I have 2 other examples, and what I will end up with instead is just to mention again this situation. Here you see that you have a Petri net with a resource R1 and another resource R2 with capacity 3 in both of them. And then there is also a connection between the first and the third sequence. And that is that, okay, C1 must have happened at least one time to make C3 possible. So there is condition that you must have at least one token here to implement C3. Well, if you see these 2 flows, or these 3 flows actually of tokens, it still looks quite readable and so on. But if you have 6 or 7 of these, and you have conditions between, say, R2 and the last sequence, then you get a lot of arcs back and forth. And you get what I call this spaghetti. But instead using variables representing these shared resources. So R1, R2, and P are variables. And to book a resource in this case means that I make an R1 minus, means that next value is current R1 minus 1. And that you can only do until you have reached down to 0. And after that, you have to wait until someone else had made an R plus, for instance, the same sequence. Here you make an R1 plus here. You see also there you have an R1 plus. So I argue that this is actually a more understandable and useful model where, for instance, these R could even be expressed. It's robot 1. This is AGV2. You can have text messages telling what these resources means in more detail. and minus in this case corresponding to the semaphore of in real-time in concurrent systems. Minus means that you step down with the semaphore until you reach 0, and then you cannot do that anything more, and that corresponds to the resource booking. You can take away 3 tokens from this R1, and then you cannot make A1 anymore. Or if you have made 2 A1 and 1 B2, then R1 is also empty. So then R1 is 0, and you cannot make R1 minus anymore. And that is, so to say, the typical restriction, which is built into this framework. So what I will show you next lesson on, actually on first on Tuesday then, is a little bit more the mathematical definitions behind this. And there are some details here which we can look at then. So by that, I would like to thank you for today. And if there are any questions more, please.
Thank you. Thank you, Professor. Any questions, participants?
Hello, sir. Were you asking me something at the start of the session? I could not hear, actually.
So, Deepojwal, we asked you to put on your, switch on your audio, that's all.
Okay, okay, yes, sir.
Yeah, maybe we should say some words about the it's called the quiz for tomorrow. Yeah, what I plan to do is to give you a number of quite simple tasks, not that complicated calculations as I've shown you in some of these, but some simple modeling and say reachability analysis and so on based on the examples you now have in the material. And then I will ask you to solve those, say 3-4 tasks. So that's what, and then you will get 2 hours to do that. And we have also agreed that I will not give any lecture tomorrow, but I will come back on Tuesday and continue this. So to get you a chance to understand this and to see also that you have got the message, I think it's nice if you can solve these small problems that I will give you for tomorrow.
Okay, so you will be having a test of 2 hours. We will be sharing a Google form with you. You will submit your responses by making a PDF and then submitting on Google form. Okay.
Yeah, or I would say it's better if you email it to me.
Okay, email it to you. Okay.
Yeah.
That would be, yeah, okay. And may I request?
And what I will do now also is that I will very quickly make some modifications here and submit today's results, because here you have a lot of some material which we can also ask some simple questions around.
Sure, yeah. So please request you all, Shubhangi, Rashmi, to please put on your videos, and I request Samir to please take a snapshot.